A tennis ball with a mass of 60 grams is served using a variable force described in the graph below. Find the total impulse given to the ball. Okay, so we're looking for impulse, and impulse is change in momentum, right? So J, which is J represents impulse, equals change in P. P is momentum, equals force times time. This is actually the formula we'd use for R5 subprocess. And the reason for this, the reason impulse equals force times time is, well, force times time. So force is equal to mass times acceleration, right? So force times time equals mass times acceleration times time. And acceleration is the change in the velocity over time. So you'd have m times change. So you'd have force times time equals mass times change in velocity, which is change in momentum. So that's why force times time equals change in momentum. Now, let's look at our system. So we're given data. The tennis ball has a mass of 60 grams. Of course, first we want to convert this into our SIs, or standard units. In physics, the standard unit for mass is kilograms. So we're just going to divide 60 by 1000, and we get 0.06, because 1 gram is a thousandth of a kilogram. You should know this by now, but if you don't, that's cool. So we need force we're using force and time. So let's see. We're given this graph here by the paper, and I only drew a very simplified version of it, but I got the data that matters, so it works. What we have here is a triangle, right? And I'm just gonna tell you now, in case you didn't know this, the formula for the area of a triangle is 1/2 base times height. So why does that matter? Like, what's relevant? Well, the area of this graph over here is equivalent to the impulse, and that's because here in the graph, well, what you could do is imagine, let's say we took the average height of the triangle. Let's say this line represented the average height of the triangle. That would be a constant force, right? So the average height is one amount for the force, right? And let's say this force was applied in 0.045 seconds. You'd have a constant force times a constant for time. So you'd get this value that makes sense. Yeah. So it just makes sense mathematically. Another way you could do this is just realize that we're looking for the average force, and since this is just a straight line, this part over here, you could take the final amount, this amount here, and the initial, and add them and divide them by 2. That's how you find averages. So it's the same concept. It's just you could understand it in multiple different ways. So anyway, let's go through with that, and we'd find. I'll do this the way that I did it. I'm just going to find the average force and multiply that by the time. But another way to do this would be to multiply this 525 times 0.05 or 0.045, sorry, and multiply that by 1/2. I'm just doing the same thing in a wrong order. So I'm just going to lay out the data first. So that's our formula over here. That's our data point. So time, we have this whole system takes 0.045 seconds to happen. 0.045, and obviously our standard units in physics for time are seconds. And the average force, again, what we're doing is we're finding the average over here on the graph, the constant, the middle, of all the values, would be, and by the way, if we divided this into two, these two triangles would have the same average because this triangle starts here and ends here, right? So the average it starts at 0, ends at 525. The second triangle starts at 525 and ends at 0. So the average, since it's just a constant line, is going to be the middle of 525 and 0 for both of them. So what I'm just going to do is take 525 and divide it by 2. So force equals, and our standard unit for force is newtons. So that would be like 262.5, yeah, 2.5. So now, what are we going to do? Well, we have all the information, and we have our process for putting the information to work. So, and this isn't work, this is impulse, but okay. Let's see. So we're just going to plug and chug, or substitute and chug, if you have Miss Robinson. Yep. Let's see. 262.5. So we're doing force times time. So 262.5 times 0.045, and we get, this is step 4, finding the solution. It is 11, so it's 11.8125, but I'm going to round it off. And this is in newtons times seconds, because force is in newtons, time is in seconds. When you multiply those two together, you get newtons times seconds. Again, not rocket science, but yeah. Well, it could be rocket science, but in this case it's not. It's tennis ball science. Yeah, so that's our answer, 11.8 newtons times seconds. And let me read, I'm not going to write this down here because that would be like, really, for you and me both, let's not go through that process. But for step 5, I just said this answer makes sense because the force was large, but the time was small. So we're not going to get an obscenely large answer, but not an obscenely small answer either. And that's what I said for step 5. And that is the answer to problem number 5.